Designers can achieve big reductions in the embodied carbon in buildings. Amy Hattan, Thornton Tomasetti's Corporate Responsibility Officer, is talking with in-house experts about how they're reducing the effect of buildings on climate change. Here's how Embodied Carbon is a production of Thornton Tomasetti.
Hi, and welcome to episode 13 of Here's How Embodied Carbon. This series explores how engineers and designers can fight climate change by reducing the embodied carbon, or the emissions associated with building materials, in the structures they design. I'm Amy Hattan. At Thornton Tomasetti, a multidisciplinary engineering and consulting firm, we've been focused on embodied carbon for over a decade, and we're channeling all of our capabilities to tackle climate change. I'm talking with colleagues about how they're achieving reductions in greenhouse gas emissions on their projects. Today, I'm talking with Meghan Kalisz, a consultant in our sustainability and resilience practice. Meghan is an expert in life cycle assessment and embodied carbon reduction in buildings, and she's currently developing an embodied carbon visualization tool. Meghan will walk us through some best practices for achieving high embodied carbon reduction targets that are based on her applied experience. Hi, Meghan. You have practical experience on a recent project with very high goals for embodied carbon. What's driving these ambitious targets?
There are a number of reasons why our clients might pursue very high goals for sustainability. But most recently, we've seen institutional projects adopt high targets for embodied carbon in pursuit of both the Living Building Challenge Core certification and LEED.
What is it about these certification programs that results in a focus in embodied carbon reduction?
For the Living Building Challenge, or LBC Core certification, a project is required to demonstrate a 20% reduction in embodied carbon from a baseline model. LBC requires us to look at the primary material assemblies. For the substructure, this includes elements such as the foundations, retaining walls, footings, and piles. And for the superstructure, it's the framing system of columns and beams and the deck system. We also look at the enclosure, curtain walls, exterior wall construction from the cladding to interior sheathing, exterior windows, doors, and the roofing.
Okay, I can see how LBC can bring a client's attention to embodied carbon. What about LEED, a very popular certification program?
LEED is similar to LBC. More specifically, with the LEED Building Lifecycle Impact Reduction Credit, it requires an evaluation of global warming potential, as well as 5 other impact categories. We quantify ozone depletion, potential acidification, which is the cause of acid rain, eutrophication, which is the flow of nutrients into an ecosystem that results in algae growth, the formation of tropospheric ozone, a smog-causing gas, and depletion of non-renewable energy resources. All these categories are very important in LEED. There are multiple paths you can pursue with the LCA for LEED certification. Path 1 is completion of an LCA analysis. This earns 1 credit. Paths 2 through 4 require an LCA analysis plus a demonstrated reduction in 3 of the impact categories, one of which has to be global warming potential. Path 2 requires a 5% reduction to earn 2 credits. Path 3 is a 10% reduction for 3 credits, and Path 4, which is the most challenging one, requires a 20% reduction in global warming potential, a 10% reduction in 2 other impact categories, and the incorporation of reused or salvaged materials into the structure or the envelope. That earns 4 credits.
Great. Using reused or salvaged materials further reduces embodied carbon in the project. But it sure is a lot for a project to accomplish. Just how do you do it?
At the very beginning of a project pursuing both LEED and LBC, we use building massing studies, BAE studies analyzing structural framing systems, and material studies to look at ways to reduce embodied carbon impact. We might study the window-to-wall ratios and look at regional material choices for reducing transportation costs. The first thing we do is a baseline study. In one project, we did a study of a steel frame with a full brick envelope and a study of a timber frame with a full brick envelope. It's not an apples-to-apples comparison, So we created a full base study that accurately modeled a steel structure versus a timber structure. There were differences in grid size, framing, decks, and foundations, but the bottom line was that the steel frame had about twice the amount of CO2 than the timber frame. When we shared the embodied carbon results with the client, we also talked with them about the cost of steel framing versus timber framing.
Okay, what did they choose?
They went with mass timber. Almost the entire building has glulam framing and cross-laminated timber decks and walls. A small area had high dynamic loads, so it required steel moment frames. In addition to considering steel versus mass timber for the project, we also looked at cement replacement as an embodied carbon reduction method.
Cement replacement. Tell us more about this option.
To help with LEED certification, the National Ready Mix Concrete Association sets regional average benchmarks for concrete mixes. For projects in the eastern region, that's a mix with about 20% cement replacement. To show an embodied carbon reduction, the project has to go beyond the baseline 20%. Because of surface finish requirements, the CLT topping slabs and the slabs on metal deck could only go up to a 35% replacement. But because our supplier had a good comfort level with high percentage replacements, we were able to push the foundation mix to 50% and even up to 70%. Once we decided on the percentages, we then had to go through the cement replacement options. In New England, fly ash and slag are the two most common cement replacements. We ruled out fly ash due to concerns with possible toxins, such as arsenic leaching out. Slag also caused some concerns for social equity reasons, primarily labor issues. This is because most of the slag in our region is being imported from China. Glass pozzolans are another less common option for cement replacement. We reached out to a supplier and had them ship up a batch so we could do a test for alkali silica reaction. We didn't have any reactions, so we got the green light for using it as a part of the mix. However, the site was tight and there was no extra space for a silo to hold the glass pozzolans. So in the end, we had to use slag. But the knowledge we gained through testing will let us advocate for glass pozzolans on future projects.
I just love that human health, social equity, and environmental impacts are increasingly being considered in building design, even if compromises sometimes have to be made. This project saw big embodied carbon reductions in its frame and slabs. Was there anything else?
Absolutely. As the project is a large building with significant facade square footage, we also analyzed a range of facade types, configurations, and materials. We looked at Western red cedar, Acacia radiata pine, Corten steel, copper cladding, reclaimed brick, new brick, and brick with recycled content. We knew we were going to use a lot of brick in the building because it would be needed to some extent to meet fire code issues. So we studied the embodied carbon content of brick. We found a brick manufacturer with a high amount of recycled material, about 20 to 40% pre- and post-consumer recycled content. We also found a reclaimed brick supplier, and because the reclaimed brick was from farther away, we also looked at transportation costs.
Transportation is a whole other layer to consider, isn't it?
It sure is. It's one thing to look at the embodied carbon content of all the materials, but when you're importing them from around the world, you want to make sure that transportation emissions aren't going to cancel out the benefits of the material. If you don't factor this in from the beginning, it can throw off the numbers for the project's embodied carbon. In the US, trains and trailers are the two most common transportation methods. The local supplier we were looking at didn't have train access. It turned out that hauling the material by trailer had a higher embodied carbon total than having it delivered by train from a supplier outside of the region, despite the longer distance.
That is not what I would have expected. What other considerations came up when looking at the building envelope?
Another thing we had to look at as part of the envelope is insulation. Initial insulation studies compared XPS, polyiso, mineral wool, and fiberglass. XPS typically has the highest embodied carbon content, but then we looked at other LCA impact categories. For example, polyiso has a lower embodied carbon impact, but it has a greater effect on ozone. We also had to optimize performance for the location of the material. So we specified XPS in the foundations, where it has the better water and compression performance. We're using polyiso on the roof and mineral wool for the wall insulation. This exercise was about selecting the best product for each portion of the building and still reducing the embodied carbon overall.
Well, it seems like you looked at every angle. Did you achieve a significant dip in embodied carbon?
We did. We reduced the embodied carbon in this project by more than 2,000 tons compared to our baseline model. The bulk of the reduction was achieved by switching the structural system from steel framing to mass timber and by using high cement replacements. But everything else, the facade choices and the insulation choices, also had an impact. It all adds up. The result of our LCA for LEED was that we had a 32% reduction for global warming potential, and we had high reductions for the other impact categories. This level of improvement really can't happen without including every major part of the building. And achieving this kind of reduction requires a client who is committed to sustainability.
Congratulations, that is a great accomplishment. One last thing, options for lowering embodied carbon often come with some upfront cost increases and require the use of unfamiliar materials and methods. How did you deal with these challenges?
Communication is the most important thing. We ran the design decisions as cost alternates, so the client could evaluate and judge for themselves the value of each option. And we made sure the design team and the contractor, subs, and suppliers were comfortable with any materials or construction methods that were outside of regional norms. It's important to supply the necessary knowledge for a new material or new detail. Glass pozzolans, for example, are not yet highly available on the market and require us to advocate for it with developers, other engineering firms, and clients. The challenge of finding environmental product declarations, or EPDs, for use in an LCA can be a factor depending on the region. Warranties can be an issue, but manufacturers are making progress all the time. We also looked in advance for market availability, or lack thereof, to head off potential problems.
So we're still learning and creating a marketplace where low embodied carbon materials are easily accessible. But with certification programs driving the work, we get to use our creativity and passion for problem solving. Meghan, thanks for sharing your story with us. Folks, there's more. Follow Thornton Tomasetti for more episodes of Here's How Embodied Carbon.